species rich in electron. So this nucleophile, always prefers to come from a sign opposite to this one. So this is called backside attack. That happens in case of SN2 mechanism. Okay, now the reactivity order for SN2 mechanism. SN2 reactivity order, it is found to be 1 degree will be more reactive than 2 degree, 2 degree will be more reactive than 3 degree. This you can easily understand. Suppose if we take a 3 degree compound here, and if we take a 3 degree compound here, so let us make it 3 degree compound out. You can make it a 3 degree compound, say here CH3. CH3, so this is also CH3, so this is also CH3. So this is a 3 degree compound. Now this nucleophile, since these are bulky groups, these are bulky groups, this nucleophile will not get required space to enter and hit this carbon atom. So that's why in case of 3 degree compound, hardly SN2 process will be followed. If it is 2 degree, that means 2 alkyl group, and in case of 2 degree, it will be 2 alkyl group and 1 hydrogen. Now what will happen? Still there will be some obstruction, but obstruction will be less compared to the case of 3 degree. Okay, so 2 degree reactivity is more than 3 degree. And if it is 1 degree, say this is our 1 degree halo compound. This is 1 degree halo compound. So why 1 degree halo compound reacts easily or the best by SN2 mechanism? It is because you see when it is 1 degree, there is only one big alkyl group. So this nucleophile can easily come and attack. So that is the reason why through SN2 mechanism the reactivity order is 1 degree greater than 2 degree greater than 3 degree. That we must remember. So once again, like this SN2 pathway that has been shown. So what is the proof? What is the support of this mechanism that I am going to say now? Suppose we start with a optically active compound. Optically active compound. Say we start with this compound. To make it optically active, say CH3, say CH3, CH2, CH2, and this one. So this is a halo compound, and here also there are this carbon is attached to 4 different groups. It will be optically active. It will be either dextro or LIGO. And what we see when we carry out reaction with this compound, we see the product also to be optically active. We see the product to be optically active. But before that, let me tell you here, we have here the condition so that it goes by SN2 pathway. So after the reaction, we see that the product to be also optically active. In SN1, we started with optically active, but the product was optically inactive. Here, we started with optically active, the product also is optically active. And this can happen only if this mechanism is So, SN1, SN2 mechanism has been said. Now let me quickly tell you the factors which facilitates SN1 or factors which facilitates SN2. So these are the four factors which determines or which influences whether the reaction will follow SN1 pathway or SN2 pathway. For example, if the alkyl halide, first factor is nature of alkyl halide. If the alkyl halide is 3 degree, SN1 will be followed. If the alkyl halide is 1 degree, then SN2 will be followed. Okay, that we have already discussed. If it is 2 degree, it can go by both SN1 and SN2. Second thing is concentration of nucleophile. If in the system nucleophile concentration is more, then it will follow SN2 mechanism. If nucleophile concentration is less, it will go by SN1 pathway. Nature of the nucleophile: if the nucleophile is a strong nucleophile, then it will prefer SN2 mechanism. If the nucleophile nature is weak, then it will go by SN1 mechanism. And last but not the least, the effect of solvent. It is seen that if the solvent is polar in nature, okay, then it goes by SN1 pathway, and if the solvent is not polar, or polarity is less, then it goes by SN2 pathway. So this is what we have discussed about nucleophilic substitution reaction. Hope you have liked my presentation. Thank you very much.